All right, we're looking now at catalyst deactivation. So we have our catalytic particles. So we have particles with active catalyst centers, and these catalytic centers may become deactivated for a number of different reasons. So, for instance, we may have some molecule out in solution, which is a which is considered to be a poison for that catalyst. So it might be that that molecule comes along and forms a bond with our catalytic center. So let's say we form a bond, and if this is a very stable bond, if it's a very strong bond that doesn't tend to break down, then we can effectively understand that this site is no longer going to be available for catalyst activity. It's no longer going to be available to reactant molecules and so on. So we can have chemical deactivation. Alternatively, if we have a situation where there are many other subparticles around, if we have, let's say, carbon particles floating about or even forming as a result of the reaction. So we could simply have carbon particles that are blocking off the site. So carbon particles or any other kind of particle or crystal that's formed perhaps by the reaction or some other process going on. So basically, if a particle comes along and basically restricts access to the site, then that's also a physical kind of deactivation on that surface. So we lose access to a site. There might also be physical reasons. So, for instance, if you have a high surface area catalyst, and you get that area by impregnating your catalytic sites on the insides of pores in your particles, then if a pore collapses, then you lose access to all those sites. So if you have a simple breakdown of your catalyst particles, then you can lose activity as well. So you've got a kind of chemical desorption, a chemical deactivation possible. You can have physical deactivation that's possible, and you can also lose structural integrity of your particle. So all those events would cause us to lose catalyst activity. And of course, if we know which one of these is tending to reduce our catalyst activity, then we can take certain steps to mitigate that. So, for instance, we could look at removing this product or this reactant molecule from the stream that enters the reactor. So that's something we haven't talked about. Let's say we've got our catalyst particles sitting in this reactor somehow. So let's say we've got some beds that we've constructed in that reactor, and we could simply try to remove any of this poison P from the stream that's passing through that reactor. So if we knew this was causing the loss of activity, then we could introduce additional separations units here to get rid of P. So if that's going on, that's what we could do. If we knew it was carbon that was depositing onto particles, or if there was some whatever kind of deposition going on there, then we could look at the chemical involved and look at some way of washing it out. If it's carbon, for instance, what's often done is there's some incineration, there's periodic incineration of the particles so that you just burn off that carbon. If you know that sintering can cause your particles to break down, then what you could simply do is use some kind of other support here. So you could use a better support for your reaction conditions. So if you know that these particles, let's say it's a fluidized bed and particles are smashing around, then you would look at using better materials for your support structure, so that there's a reduced likelihood of the loss of pores and hence the loss of catalytic centers. So there are various things you can do once you know what's causing the loss of activity. So that's one kind of macro thing that you could do. Another important thing to understand is the time scale over which we are losing activity. So if we are losing activity on the order of hours, let's say you lost activity over 1 hour, then you could look at, let's say, a periodic regeneration of that catalyst. So you could look at some way of periodically withdrawing catalyst, reactivating somehow, and then reintroducing that catalyst to your reactor. So we'll talk about regeneration loops later. So regeneration is a possibility. In other words, as part of your process, you include regeneration possibilities. So that's what we would do if we have a short time scale for the catalyst deactivation. If we have a longer scale or a slow deactivation, perhaps that's on the order of years, right? So if it's on the order of years, then we would consider instead changing operating conditions. So in the case where the loss of activity is on the order of years, it wouldn't make sense for us to have all this apparatus in place. We would rather look at changing how we operate that reactor such that we maintain a constant reaction rate there. So that's a possibility that we'll talk about in detail right now. And if you look here in the notes, we've got this possibility outlined. So here we are talking about trying to retain the original catalyst activity. So we can say that in our reactor, let's say we've got two restraining plates and we have our catalyst in this reactor, and we know that we are going to lose activity over something like, let's just say, 2 years. Now, we don't want to, if it's going to take 2 years to deactivate this catalyst, we don't want to go and introduce regeneration loops and so on. We would rather look at operating such that we achieve a higher reaction rate here. And of course, when we lose activity, right, let's represent activity as a little a, and that's in time. So when we say we are losing activity over a period of 2 years, we do not mean that we'll be operating at perfect activity until 2 years, and then we lose all that activity. So, of course, in terms of what we described here, this is going to be a continuous process. So continuously we might be blocking off pores, or continuously we might be getting coke depositing slowly. So what will actually happen is that we will lose this activity over time. So we lose activity as time goes on. And what we would rather do then is to quantify this loss of activity. So if we know how fast we are losing activity, and if we know that activity as a function of time, then we could look at operating this reactor such that we achieve the same reaction rate as we had initially. So remember, in any chemical process, we really would like to operate as stably as possible. So that means that we will be operating with the same flow rate. We would like to fix a constant flow rate through the system. We would like to have the same conditions through here also. So we would like to maintain a particular a particular concentration at the inlet point. We would like to know what concentration is coming out here. So those things are important because, you see, we are being supplied by some stream here, which depends on upstream units. And we don't anticipate that we are going to have this whole process now responding to what's going on in these particles. We would rather expect that these things are going to be constant. Likewise, going out here, there are downstream units. There are distillation columns and other types of separators and so on. So we anticipate that we would like to maintain these concentrations and so on just as they are. So, given that those things should be constant, we should only consider things that just change what's going on in this reactor locally. And so we become you could say that we are trying to identify what variables we can use to accommodate this loss of activity over 2 years. So we accept that after 2 years, we have to do something more drastic. So after 2 years, yes, we do have to look at the shutdown and replacing this catalyst and perhaps regenerating it offline or something. So without having constant regeneration, every 2 years, if we have to regenerate, that's acceptable. So we have that possibility. We are going to regenerate, but what are we going to do continuously, given that we are going to lose activity over time? So one thing we could propose is, well, let's change the temperature. So if we change the temperature progressively, if we increase it progressively, then we are certainly increasing the primary reaction that's going on here. So of course, we've got some primary reaction that we are trying to catalyze. So even if it's a simple one like this, A goes to B. Let's say the reaction rate is kCa, so it's a simple first order reaction. So we are saying here Ra dashed equals kCa. So this is all well and good if it's a non-catalytic reaction. But of course, now we have this catalyst that's going to be losing activity over time. So let's introduce this A here. Let's say this is kCa times A. And so initially A equals 1, and so we have a nice high reaction rate. And then as time goes on, A becomes less than 1, and it starts tending to 0. So as A drops, then the observed reaction rate drops. And of course, we don't want this to happen. We want to change the temperature in here. And if we do that, then we are going to increase this reaction rate. So K will increase. So we want to choose temperatures such that we achieve that nice high initial reaction rate. So let's try and work out a relationship for that. So let's say Ra dashed is kCa times A. Well, that's the same as we have there. And we know initially A equals 1. So we can say Ra dashed at T equals 0, right? At T equals 0, A equals 1. So we can say this is K, and that's going to be at T0. And that's times Ca. And then that's going to equal Ra dashed at some future time t. So that's going to be some other k value. So that's going to be k at some time in the future t, multiplied by Ca, multiplied by the activity at that time t. So your A here equals 1. That's why we don't see an A here. Here we don't know what this A is as yet because we haven't specified a way to determine this. We don't know as yet how to get this curve. But anyway, it will be some number. We hope we can find out what it is. But anyway, just assuming it's some number for now. Looking at these two parts of the equation, we can say, well, those are the same concentration. We had specified that this concentration and this concentration should be the same. So let's accept that we can cancel these two. And so we can rewrite this. We can say A at time t must equal k, the initial k at t naught divided by k at time t. So that's one relationship that we can write, and let's look at the way we've done it in the notes here. So you can see here we are saying that at the initial time there will be some initial temperature T naught, and we want the reaction rate to be the same as what we had for those conditions. So we had some reaction rate initially for that temperature, and then at some future time t, given that we've got some future temperature t at time t, that rate must equal that initial rate. So we are choosing this future temperature such that we achieve that initial rate. So this future rate will equal the activity at that time multiplied with the rate that we would have at that temperature. So that's what we've developed just now, right? So we can say then that the reaction rate is equal to, right? So that rate is generally equal to KACA. So we know this is generally true. So we can rewrite this and we can say this is equal to that form. So that initial rate, right? This was equal to K at T naught multiplied by CA, and that's equal to A times KCA. And so if we can cancel the CAs and we can expand on each of these Ks using the Arrhenius expression. So this is the K at temperature T naught, and that's the K at temperature T. And then we've got that A of T there as well. So you can see now we have a nice relationship among the temperatures and the activity. And we can, of course, take the logs on both sides. So we can cancel a reaction, the pre-exponential factor for Arrhenius. That's going to be the same, so we can cancel that, leaving us with these exponentials. And if we take the logs, again, the activation energies can cancel. The universal gas constant R can also cancel, leaving us with 1 over T naught. And if we take this across on this side, we can write that as 1 over T naught plus R over EA ln A being equal to that future 1 over the future temperature TT. So already we have a nice relationship between this future temperature, the initial temperature, and the activity at that time T. So that's one relationship that we can establish straight off, and that just comes from recognizing the future rate in terms of the activity as compared with the initial rate. So that's equation 1. We can park this result. The next thing we want to do is elaborate on this A here. So we need to specify how we are going to lose activity if we are going to get if there's any hope for us to find what temperature we need to establish. So that's what we are trying to do now. We are trying to work out what temperature do we need to apply in the future if we want the rate to stay the same. So we need this A here. That's the unknown currently. So let's say that our activity is being lost in this way. So we are losing activity because of surface dynamics. So we recognize that we have our primary reaction going on. So we've got our catalyst. We've got A out here. It comes along to the surface, and we've got B going off. So that's what we'd like to happen. But at the same time, something else is going on. So you could think of another little circuit here that our catalyst, that is being converted to something else. So while that's going on, in parallel, we've got some other reaction going on that's causing our activity to be lost. So in the same way that we can write Ca, Kca for the reaction rate in the loss of A, we can also write some other rate expression for the catalyst. So we can say Ra is equal to some deactivation rate constant multiplied by, and instead of a concentration, we'll use A as our kind of surface concentration of sites or something like that. So we said that A is some fraction that tells us the amount of sites that are available. So here it's a kind of concentration. So we can treat the activity loss also using a reaction rate expression. And so that's what we are doing here. So we are saying the rate of change of active sites equals the loss due to the deactivation reaction. And so we are taking a KD times, and then we are just saying we don't know what the reaction order is. Let's just for now say it's N. So this is an nth order loss of activity. So we could propose anything here. This is, you could say, just a case study. So taking this example where these are the dynamics for the loss of activity, we can progress from here and look at how our temperature must change to keep the rate the same. So whatever our catalyst dynamics are, we would put them in here as the catalyst deactivation kinetics. And so in this case, that's what we've chosen to pursue. So if that's our kinetics, if those are the kinetics for deactivation, then we can expand on this. We can say, well, the deactivation rate constant should follow an Arrhenius expression as well. And so here's the pre-exponential factor and the activation energy and so on. So that's what we have on the catalyst side. And so if we if we now look at solving this, we can say, well, first of all, we don't know what the temperature is going to be in the future, because this temperature we are changing such that we overcome this activity loss. So we don't know this temperature. We would like to integrate this equation. It would be great if we could just integrate this equation, and then we'd get A as a function of time, and we could just stick it in there and get the temperature. The problem is that the temperature itself is changing because of activity itself. So, but of course, we have this relationship. So we do have this relationship that we got from trying to keep the rate the same. So we could simply substitute this future temperature in for temperature here. Excuse me. So substituting the temperature in here, we get that expression. And now you can see that temperature has vanished in this factor. And there's no temperature out here, no temperature out here. Everything else is, well, that's not a constant. So anyway, so we've got this now. And we could integrate this, and that would give us A as a function of time. And then we can substitute that and get temperature. Here, it's just pointing out that, let's say we were losing activity due to sintering of the catalyst. So earlier when we were saying that perhaps the pores are breaking down and the particle is breaking up, then that's the sort of thing that happens with sintering. So if it's sintering, that tends to be second order, and so n equals 2, and so let's say it's sintering, right? So n equals 2, and we've got this nice expression now. And if we just look at this equation, you can see that a couple of things can cancel here. Excuse me. So first off, we could just say, let's split off this part here. So this 1 over T naught multiplied with E over R, that's basically the Arrhenius constant at temperature T naught. So we could just split that out as a KD at T naught, leaving us with this stuff in here multiplied with that. So if we multiply these out, the R's can cancel, leaving us with ED over EA, and then ln A here and A squared. And of course, we can take this. So since this is the log here, you can take the factor in front of a log as the power of the argument. So that's what's happening here. And then we are taking the ln of, or the exponential of a ln, which we can just take as the argument here. So this operation results in just this thing, and then we have to multiply by A squared. So we can just add together the exponents. So it's 2 minus ED over EA. So that's how we get to this form down here. So now we have dA dt equals this thing. And this in front here is just a constant. This is the kinetic constant at a specific temperature T naught, which is also constant. So that's all nice and constant. So we just have to integrate for this A. So as long as 2 minus ED over EA, as long as that's not equal to 1, then we can divide, we can say dA over that equals that times dt, and we can integrate that equation quite nicely, and we can integrate it and get that form. So that's the solution if we want to integrate this equation. So for the second order activity loss, we can easily get activity as a function of time. So unfortunately, the way I've written it here, it's time as a function of activity. It's a bit of a silly way to do it, but anyway, you can easily repose this in terms of activity. So you can say we now have activity as a function of time. And of course, if you have that, then you've got this this expression here, equation 1. So we can just stick in activity. So for any time in the future, we can work out the activity, get the value there, and that will tell us what temperature we need to apply to get the same initial rate for that reactor. So that's all we do. And here's an example. I think it's something in Fogler. So for these activation energies and that that pre-exponential value, we find that this is the temperature required over 2 years. So in order to maintain the same initial reaction rate, we have to ramp up the temperature like this over time, over a time of 2 years. So going from 625 Kelvin to close to 700, that's quite easy to do, right? We are only increasing temperature by 75 Kelvin over a period of 2 years. Should be quite doable. So you could also say that the material safety also guides you as to how long you could keep doing this. So for this strategy where we just increase temperature to maintain activity, we can look up, what's the tolerance of my materials for this reactor. So if my reactor can only tolerate 800 Kelvin, then I would look at, then let's just integrate this equation and see when we're getting to 800, and then say, okay, we can tolerate increasing temperature for that number of years. And so that's what we could do. So this is the strategy that we can apply if we have a slowly deactivating catalyst, right? We just improve conditions in that reactor to achieve a better rate. Excuse me. So the other possibility we said was that the deactivation was quite fast. So if we are losing activity very quickly, then we do have to keep regenerating that catalyst. And here is a nice solution to that. So this is a regen reactor. So you can see here's our primary reactor. You can see we are feeding in our reactant here, and we are getting out a product here. So here's your primary reaction loop, if you like. We can see here catalyst is falling into the reactor. So we've got catalyst and reactant moving co-currently through this reactor. And the catalyst falls out here, and the product goes off there. So now, of course, the catalyst is falling out here, and it's going to be regenerated. So somehow we are regenerating catalyst. So this is probably a situation where we have some kind of coking happening. So we've got physical deposition of carbon or something else on those catalyst particles. So the particles falling out here are probably coated with some kind of soot. And here we are blasting air through. So we are blasting the air, number one, to push the catalyst particles back up here, and also to combust those particles. So if we are applying combustion conditions here, then while those particles are being blasted back up here, we are also burning the carbon off those particles. And so we have regenerated catalyst particles here that can then fall in with this cohort of reactant molecules, if you like. So you can see here's a catalyst regeneration loop, right? Fresh catalyst in here, then the catalyst as it's reacting gets coked, and then the coked particles are here, where the air is blasting it back up here and burning off the coke as it does so, and then we've got the fresh catalyst again, the refreshed catalyst, I should say, falling back in again. So that's quite continuous. The way I'm describing it kind of implies a cohort, but of course it's not like that. So while particles are falling through here, there are other particles already being lifted through here. So we have a constant flow of particles through this reactor here with a constant flow of feed. So you can see in this way, we maintain nice stable operations. There's no cycling of anything here. It's not like we are waiting for anything to happen. We are constantly feeding in regenerated particles here and constantly getting a stream of product out here. So this can all operate quite nicely and steadily, and that is a continuous process. So that's a regeneration reactor. So that's the solution you would apply if the catalyst particle is deactivating too quickly for the change in temperature style solution. You would also tend to find this solution in the older refineries. So you'll find in this fluidized cat cracking reactors, right? Yeah, I guess here. So in these fluidized cat cracking reactors, you often had this problem of spent catalyst. So you have your, I guess, here's where we are actually feeding the reactant in with the catalyst. So that's coming through here, and then your catalyst is getting spent. So your spent catalyst falls out here. It's regenerated here, and then it's blasted back up here into the reactor. So you've got that constant catalyst loop here, and you've got your reactor cycle going on. Here you can see a combustion air for the regeneration. So now, of course, over time, we find better and better ways of regenerating that catalyst. So it was the case that in the past, the regeneration would happen in this vessel. So today, the regeneration is done so efficiently that, in fact, the regeneration happens, I think it's in one of these lines. So the regeneration is happening in the riser line, something like that. So in fact, today, even though most refineries still have this kind of unit, this regen unit, actually no regeneration is going on there. It's actually in the pipelines that they manage to regenerate the catalyst. You'll find in chemical engineering many artifacts from previous processes that still survive in the current process. So that's just the lag between research and development and improvements in the process, and the fact that the refinery already has that unit in place. And sometimes it's almost like superstition that they just maintain those units on site. So that's a regen unit. So that's a quickly deactivating catalyst type of strategy. Now, of course, we want to model this, so we still need to be able to predict our reaction rate, and we can see that it's not a trivial job to model these reactors, because even though this regeneration is going to happen, we have to acknowledge that what's going to happen is, well, it's a couple of things. One is, first of all, you've got these particles that are falling through the reactor. So we've got a constant feed of regenerated particles that are falling through here. So we've got some regen loop going on. So you've got your newly regenerated catalyst particles entering and then falling out down here. And of course, as they are falling, they are picking up whatever it is that's causing them to deactivate, or they are just deactivating. We don't have to specify the nature. We know we are losing activity quickly. So we are losing activity as it's falling. That means as we look down this tube, we are seeing a loss of activity. So let's call Z the axial distance down this tube. And we can say then that activity is a function of Z, right? We are losing activity down this tube. At the same time, we've got our primary reaction going on. So we are feeding our reactant in, Ca in here, and it's reacting. So fine, we are losing activity, but we still have some activity wherever we look. And so we are reacting, we are converting A to the product as that's falling. So both those things are happening simultaneously. So we need to be able to predict this exit concentration Ca, given that the activity we are seeing up here is not the same as the activity down there. So let's look at modeling this reactor. Let's see how we can predict the exit concentration in the face of this complication of losing activity while the reaction is happening. So let's just start with a plug flow reactor. So we can write our basic design equation. So just on the reactant side, we can say we've got the conversion changing as we consider different weights of catalyst. So now remember that this is a constantly moving bed of catalyst. So we could count our distance down the tube in terms of Z, or we could count it in terms of the mass of catalyst. And we assume that our catalyst is moving quite regularly through here. So if we say, okay, for 1 kilogram of catalyst, there's going to be a certain Z position, and then for 2 kilograms of catalyst, there's a certain other position, and so on. So we could characterize the distance down this tube in terms of the weight of the catalyst or the mass of the catalyst. In other words, that's the mass of catalyst, the cumulative mass of catalyst up to a certain point. So counting from here to some other position, there's a certain mass of catalyst. So we can say X is changing with the catalyst mass, and it will change according to the reaction rate, where that reaction rate is equal to the rate we get right at the top multiplied with the activity at that specific point. So for a given position, we can say it's a Z position or it's a W position. We can also say it's a time position. So it takes a certain amount of time for particles to chug their way down here, right? So these particles aren't just falling free like this. There's a whole bed here that's moving, and it's going to move at a fixed speed. So there's for us to consider a particular position here, there's going to take some time. Maybe it takes 20 minutes to get down here, and then 40 minutes to get there, and so on. So that's what this is trying to say. So we have some reaction rate right up at the top, and we've got some activity at that position at some time down this tube. So that's your local reaction rate. That's the rate that you are getting at this position. So let's look at this position. At this position, we've got a specific reaction rate here, which will be different to the reaction rate here. This rate will be higher because you've got a higher activity. You've got a lower activity and hence a lower rate here, and so on, a very low rate down here. So that's rate as a function of time down the tube. And then we can say, well, if we can consider time also as another variable down this tube, then we can write our activity dynamics, our deactivation kinetics, we can write them in here. So in the similar case where we looked at slow deactivation, we can also look at this fast deactivation case, and we can just solve this equation, and that can give us activity as a function of distance down the tube. So that's what we are doing here. We have these two equations now. So you can say this is about our reactant, and so that's conversion of the reactant, and this is a different equation. This is the activity in the particles, And of course, now we've got two different independent variables here. Here we've got weight of catalyst, and here we've got time spent falling down that, falling with that bed. We would like to integrate these two equations simultaneously. So we can easily do that, right? We could say, well, that catalyst is falling at a specific rate down that tube. So if we look in this tube, we can say that there exists some speed at which that catalyst is falling. So U is some value in, let's say, kilograms per second. So we are feeding particles in at U kilograms per second, and up to some point here, there's W mass of catalyst. So we can say that the time taken to reach that position is that mass of catalyst divided by that mass flow rate of catalyst. So mass divided by mass flow rate is going to give us time. So that's going to give us the time spent reaching W of catalyst mass. So that's how you can work it out. So it's the same concept as space-time, right? Remember, in space-time, you take the volume in the reactor and divide it by the volumetric flow rate, and that gives you the average time spent in the reactor. So this is the same idea, right? We've got a certain mass of catalyst in this section, and we know how fast that mass is moving through. So you just take the mass here divided by the mass flow rate, and that gives you the time taken to reach that point. Right, so that's how we can get a time, and that's how we can get rid of this extra independent variable, this t here. So we can say dt equals dw over us. So us, the mass flow rate, that's of course going to be the same. So no matter where you look, you'll be able to say, well, the catalyst flow rate, if it's 12 kilograms per second here, it must be 12 here and 12 there and 12 there and 12 there. So it's the same mass flow rate. So that's a constant. US is a constant. T and W, those are the variables, so we can say this. So now that we have this, we can replace this dt over here with this dw over us, and so we can rewrite this expression like so. So now we have these two equations written in the same way. So we've got this equation now from here, and then here we are just rewriting that expression. And this is now a complete set of equations. We can see that these are coupled equations. Well, maybe this one's not coupled, but this one is. You can see dx dw, that does depend on the activity itself. So it's coupled through that, and so we need to solve these things simultaneously, and we can get the activity and the conversion. And maybe just as a sample, if we plot that here, okay, if we plot that as a function of w, so we would expect that the conversion would rise. So conversion would rise, and your activity would drop. So as activity drops, the reaction rate goes down, and then conversion doesn't increase as fast because we are losing activity. So those are the results we expect for solving dx dA and dx dt, dx dw, and dA dw. So all you have to do is stick in your catalyst deactivation kinetics here. You stick in your primary reaction kinetics here, solve them simultaneously, and you'll get that solution. Okay, so those are the two the extreme scales in terms of activity, and those are the strategies we can use. We can change the operation in the reactor, or we can look at regenerating our system.